So this is the second meeting on the chapter 12 review on the Lewis structures. So we will do HCN and the sulfate ion. So HCN, we need to decide if it's a covalent compound or an ionic compound. So let's look at the periodic table. So we have H, C, and N. So hydrogen, atomic number 1 in group 1A. Carbon in group 4A. And then nitrogen in group 5A, just next to carbon. So they are all in group A. And so that means the group number can tell you the number of valence electrons. So hydrogen is a non-metal, even though it's on the left side of the periodic table, it's a non-metal. And it has 1 valence electron, being in group 1A. Carbon has 4 valence electrons, being in group 4A. And nitrogen has 5 valence electrons. So these are 3 non-metals altogether. So they are making a covalent compound. So that's a covalent compound. So let's count the total number of valence electrons. So we have 1 from the hydrogen, and there is only 1 hydrogen, plus 4 from the carbon, plus 5 from the nitrogen. So that's 10 electrons to distribute in that structure, 10 electrons in total. So now let's position the atoms. And here, the way they are listed in the formula is the way you want to position the atoms. So hydrogen first, then carbon, and then nitrogen. So, the hydrogen being, the first atom in the periodic table, hydrogen is an exception. It doesn't want an octet, it wants a duet. So let's write this duet. Hydrogen wants a duet, which means just 2 valence electrons around it. It likes to be like helium, and helium has 2 valence electrons. That's an exception among the noble gases. And so hydrogen only wants a single bond. And so when we are doing the single bonds now, we satisfy hydrogen by doing this single bond between carbon and hydrogen. And so because of that, because hydrogen, just like the halogens, they want to have only 1 single bond. So they will always be on the outside of your structure, never in the middle. So they cannot be hydrogen and the halogens, they cannot be central atoms. So here we have used 4 electrons by doing 2 single bonds. So let's calculate that we have 10 electrons minus 4 electrons from the 2 single bonds. And so we have still 6 electrons to distribute. So still 6 electrons, and hydrogen is already satisfied with its duet. This is very important here. The duet is done. So the 6 valence electrons left over will have to go to the nitrogen next, because you want to start with the outside atoms first, and nitrogen is the outside atom. So you want to distribute lone pairs to nitrogen. So 1, 2, 3, 4, 5, 6. And that's using all 6 electrons here. Notice how we had 6, 6 minus 6 equals 0 electrons left. So there is no more electrons left to distribute. And the nitrogen right now is happy because 6 electrons from the lone pairs plus 2 from the single bond, that's 8 valence electrons around it. However, the carbon is not happy because it has 2 electrons on one side, 2 electrons on the other side, so that's 4 electrons around it. That's not an octet, it's only 4 electrons in total. So, and we cannot bring more electrons, right? We've used them all. There is no more electrons left. So when this happens, one of the outside atoms needs to share a lone pair, and here only nitrogen can share a lone pair. So you will need to share a lone pair from the nitrogen towards the carbon. But by doing the sharing of only one lone pair, that brings the total for carbon to 6 only. So nitrogen will actually have to share 2 lone pairs. So then we need to rewrite everything. And so let's rewrite this under. Let's rewrite hydrogen. So I have redrawn the hydrogen bonded to the carbon, bonded to the nitrogen, and we still have a lone pair on the nitrogen. And 2 of the other lone pairs have been need to be shared now. And the arrow is pointing towards carbon, but really they will be in between. So what we need to do now is to change those lone pairs into, you know, double bond and then triple bond between carbon and nitrogen, right? The arrow should be really going into the middle between the two. So there we go. We have the arrows showing how the lone pairs are redistributed from lone pairs to the nitrogen as triple bonds. So now we have a triple bond between carbon and nitrogen because nitrogen has shared 2 lone pairs. And so if we count the number of atoms of electrons around carbon, we have 6 electrons with the triple bond. That's 6 electrons because, you know, one line is 2 electrons. So one line, 2 electrons times 3 lines, that's 6 electrons, you know, in the triple bond. 6 electrons on the right side of carbon plus 2 from the single bond with hydrogen. That's 8 valence electrons around carbon. So here we have an octet. And we already said we have a duet for hydrogen. And then nitrogen, again, 6 electrons between the nitrogen and the carbon, because these are shared between carbon and nitrogen. So they count for both the carbon and the nitrogen. And then you add the lone pair, so 2 more electrons, that's 8 valence electrons on the nitrogen. So we have, all atoms have their octet or duet. Here we can write octets are satisfied. And duets. So now we need also to check that, we also need to check that the total number of valence electrons is 10, like it should be. So let's count that. We have a single bond, one single bond, and that's 2 electrons, you know, 2 electrons, plus a triple bond, one triple bond, and that's 6 electrons, plus a lone pair, one lone pair on nitrogen. So that's another 2 electrons. So we have 2 from the single bond plus 6 from the triple bond, that's 8, plus 2 from the lone pair, that's 8 plus 2, 10. So we do have our 10 electrons in total, and that's the correct total we should have. So that means the Lewis structure for HCN is correct as it is here. So now we will do the sulfate. SO4 negative 2 is the sulfate ion. It's not formatted properly because I cannot write the 4 in subscript and I cannot write the 2 minus in superscript. But yes, this is the sulfate ion. So we see that sulfur and oxygen are both nonmetals. So that's a covalent, covalent bondings between them. Let's look at the periodic table to know how many valence electrons we have to distribute. So we have oxygen from group 6A, and we have sulfur also from group 6A. So they both have the same number of valence electrons to start with. And again, they are both nonmetals, so that's covalent bonds between them. So 6 valence electrons per oxygen and per sulfur. So let's calculate the total number of valence electrons we have to distribute. So we have 6 electrons for the sulfur, and there is only one sulfur. That's a sulfur, yeah. Plus 6 electrons times 4 oxygens. Plus, so this is a polyatomic ion, right? We see how we have 2 negative charges here. So those 2 negative charges mean you have 2 electrons in excess, 2 electrons that are not cancelled by protons. So you need to add them to the total. So they will have to be added inside here, and so plus 2 electrons, from that negative charge. So that's a total of, so 5 times 6 is 30 plus 2, it's 32 electrons in total for this structure. So now you want to position the atoms relative to each other. And here, the central atom will be the sulfur. So because it's 1 sulfur for 4 oxygen, so the sulfur will be in the center because molecules, as we said, tend to be symmetrical. So let's place sulfur in the center here. And then oxygen, 1 oxygen on each side. So we have 1 oxygen on each side of sulfur because there is 4 oxygens. So that's how you want to position your atoms. The second step is to draw the single bonds between the central atom and the outside atom. So let's do this. And so make bonds, single bonds between the sulfur and each oxygen. And then we will count the number of electrons we have used. So we have used, so out of 32, we have used 4 bonds with 2 electrons each. So 4 times 2, 8 electrons. And that's going to be 24 electrons left. So we still have 24 electrons to distribute. So those 24 electrons left need to be distributed as lone pairs on the outside atom first. So we will do lone pairs, and we will start with all the oxygen. So because each oxygen has a single bond, so right now they have 2 electrons around them, and they want 8, they want an octet. So then we draw 6 dots around each oxygen, and this way 6 electrons plus the 2 from the single bond, that's going to be 8 valence electrons around that oxygen. So we do that to each of them, and we can see that we have enough because 4 times 6 is 24. So that means we will use all the electrons left over to do those lone pairs on the oxygen. And so each oxygen will be satisfied because they will have an octet. So this way we have used all our electrons. So we can count that 24 minus, 6 times 4 oxygen, 6 electrons per oxygen, and that's 24. So that's 0 electrons left. So 0 electrons left at that point. So we have no more electrons left to distribute, and we can check here that each oxygen does have an octet, right? They each have 6 electrons from the lone pairs plus 2 from the single bonds. That's octets of valence electrons for each oxygen. If we look at sulfur, it has 4 single bonds around it times 2 electrons each. That's also 8 valence electrons around the sulfur. So actually sulfur also has its octets. So we can write that octets are all sets. They have been done for each of them. The second thing you want to verify is that the total number of valence electrons in the structure corresponds to 32, like what you should have. So let's count that and let's write it. So we have 4 single bonds, 2 electrons each. So that's 8 electrons plus, so if we count the lone pairs, there is 3 lone pairs per oxygen, and there is 4 oxygen. So 3 times 4, 12, and times 2, because there is 2 electrons per lone pair. So that's, let's write this differently. Let's put it 6 electrons as lone pairs, 6 electrons from lone pairs on 4 oxygen. So that's 4 times 6, 24 electrons. So 24 plus 8, that's 32. So we do have the total number of valence electrons. It's a correct number. So because this is an ion, right? This is a polyatomic ion. So and it's in particular a negative ion, but we also do that for positive ions when we are doing Lewis structures. We do what we call brackets. So we do brackets around the whole structure, and then we specify the charge in the upper right corner. And so let me make it in red so that we see it well. So 2 minus, this is a -2 ion here. So that's how you finalize a Lewis structure for a polyatomic ion. So we have checked that we have an octet for each atom, right? They each have an octet. We have verified that the total number of valence electrons corresponds to the number of electrons we had to start with. And for polyatomic ion, you want to have the brackets around the ion with the charge in the upper right corner. And so that finalizes the Lewis structure of the sulfate ion.